This is essentially part 2 of my discussion on benzene substituent effects. And I've discussed the entire introduction and the impact and the meaning of this on part 1. So you must watch that first. If you already did, then welcome here and we will proceed. So, what we should have discussed before is the fact that the moment that my benzene ring has one substituent, that one substituent will have an influence on the overall reactivity of the ring. It depends really on what that substituent does. If I have a benzene ring wherein my substituent question mark gives electrons to the ring, I call it an activator. It's like saying that electrons, negative charges, are what fuel benzene in terms of activity. And therefore, if I do the opposite and I have a substituent which will get the electrons from benzene, we call that a deactivator. Wherein we can imagine some parts of benzene, remember, electrons are going out. So meaning some part of benzene is being more positive. And since benzene, remember, is active because it's nucleophilic, if it's negative, it's active. Therefore, if it becomes a little more positive, then it must be inactive, which makes sense on a logical standpoint. So activators are usually those that give electrons to the ring, right? And they do so by various mechanisms, some of them by continuous pi resonance, some of them by hyperconjugation, and some of them by lone pair delocalization. For the activators, there are also various ways by which electrons can be pulled away from the ring, such as mere brute electronegativity, electron withdrawing inductive effect that is, or partial charges, or even entire positive charges. And we will try to examine now how those influences on benzene direct the movement of a second or even a third substituent. In order for us to do that, we just need to clarify one more thing, that if I have, for example, my first substituent and this would be carbon number 1, the positions related to it or relative to it are the following. Next to this carbon are two ortho positions. After the two ortho positions are the two meta positions. And opposite to the carbon here is the para position. And we need to acknowledge those positions and call them and identify them properly, or otherwise everything that we will be discussed is a jumble of confusion. So, well, we already have this ring on the left. Let's start discussing this example first. Do note that an aldehyde group, a formyl group, is listed as a deactivator. So why again exactly? Well, again, that is because of the fact that if I have a carbonyl group, this carbon will be attached to O, which is electronegative, making O partial negative, making this carbon partial positive. And remember that in order to quench this kind of charge, it must be uh, kind of cancelled out by electrons, and the electrons would come from none other than the benzene ring. So in order to make this more concrete, we have to go back to our traditional arrow drawing, really more of seeing really the truth behind what I will say later. So we can imagine first that this bond here will be going here, and then as a response, this pi bond from the double bond O will go here, and then as a response from the benzene point of view, this double bond will proceed here, and this double bond will proceed here. That's a lot of arrows, right? But following all the arrows, it will be like this. Again, this oxygen will now be negative, this will now be a single bond, this will now be a double bond, then this thing right here will be drawn like this, then this one moving to this side will become like this, and the fact that this carbon right here has no more double bond with it, meaning that we now have a positive charge at, what position is this? Beside this carbon, right? So we have a positive position on the ortho carbon, on one of the two orthos. Now, in order to see all possibilities, we need to imagine what are the other possible resonance structures of this. Well, we can imagine that this bond will only be moving here and all these other bonds remain the same. So if I do that, it would now look something like this. And now our positive charge will lie on this carbon, which is a para position. Or maybe one more time, you can imagine this double bond going here, and it will now look like this. In that case, your positive charge will lie here, and this is actually just the other ortho carbon. So what do we see here? You notice that the meta position doesn't really have any change going here. So for meta, let's just put this as like a flat line, meaning there's nothing that happened. But what does it mean if something here becomes positive? Well, remember when I told you this a while ago, anything that becomes more positive becomes less active. That means that the activity of the ortho, both ortho and para positions have gone down. Meaning that my ortho and para product possibilities go down because the activity on those carbons go down based on our resonance structures. And that means that my R is less likely to go to ortho or para, giving us no choice but to have more possibility for the meta position. All I'm trying to say here is that most of our deactivators will also direct any second substituent to the position meta. Again, let me repeat that. Most deactivators are meta directors. But I said most, right? Because there is one exception. The reason for the exception I will not anymore cover here, but halogens are actually not meta directors. Yeah, they are deactivators, but they are the only deactivators that are ortho and para directing. Okay? I'll get back to this in a bit. For now, let's try to examine what would happen if instead of a deactivator, we have an activator like OH. Remember that OH is an activator simply because it is something that gives electrons to the ring. And so, in that case, OH's method is by electron, specifically lone pair delocalization. It goes here, this lone pair goes to this bond, and as a concerted response, all of this would move. Okay, following that, it would now look something like this. This would have a double bond that would give my O an excess bond, making this positive. Okay, and then the double bond here a while ago will now be here. The double bond here a while ago will now be here. And the double bond here a while ago will be concentrated on this carbon as a negative charge, particularly on the ortho position. And maybe I can speed this up. Following what I did a while ago, let's try to draw all possible resonance structures. So maybe what I can do here is move this here, and then maybe this one will move here, okay, and it would look like this. So now, my negative charge has the possibility to be concentrated on this position, which is, if you can still relate to this carbon, para, and then one more, we can imagine this negative charge going here and this one going here. Wow, we're running out of space. But it would look something like this. Okay. And the negative charges here. Oh, I forgot those. Okay. And here, now, my negative charge lies on the other orthocarbon. This is the first orthocarbon. This is the second orthocarbon. So, notice that, well, once again, our meta is kind of playing it safe. Our meta position did not really become more active or less active. It was neutral. But now look at this. My ortho, both ortho, and para positions became more negative thanks to our activator. And what does being more negative imply? It implies that this time, activator, right? This time, our ortho and para positions are more active than or are more, let's say, electron dense compared to the meta position. So now the tables have turned. Now, my R has more possibility to go to the negative uh, carbons. When I said negative, the carbons of higher electron density, which are none other than these two positions. Okay? And yes, two, meaning there's some of them going to the ortho, some of them going to the para. Super little would go to the meta. If there is, it would be minimal. Okay? And therefore, that concludes that all, now this time I'm using the word all activators are ortho-para directors. I'm saying all because we normally don't find in textbooks any exception to this. Okay, so remember, most ortho-para directors are activators. And again, don't forget, we have one class of the activators which are also ortho-para directing, which are all the halogens, including fluorine, chlorine, bromine, and iodine. So now, what's this all about? How can we use this? Before we continue with that, let me just say that we have additional reactions to just complete the lineup of reactions for benzene. We will get back to the usage of the directors in a bit, but let me just shortly interrupt that with these reactions. These are very simple, and in fact, this won't take a lot of time. Um, Let's start with the first one, benzylic oxidation. So first, remember when you say benzylic, it's the carbon that is next to the benzene. So if this is benzene, whatever carbon is located here is called a benzylic carbon. And as long as it's any alkyl group that is not quaternary, meaning if it's primary, secondary, or tertiary benzylic carbon, if I subject this thing to KMNO4, then that will automatically become COOH. Regardless if it's 2, 3, 1 carbon, 5 carbons, 10 carbons, we don't care. As long as it's not a quaternary benzylic carbon, it's gonna become COOH. Okay? Actually, it's some type of oxidative cleavage, and that explains why it doesn't matter how long it is, because you can just imagine getting some scissors and just cutting that carbon, and it will all become one carbon at the end anyway. Okay? So that's the long story short. You get a product which is, well, we call this benzoic acid. Okay? If I have a nitrobenzene like this one, I already discussed to you in one video how to get nitrobenzene, and that is by plain nitration. You can actually reduce the nitro group using H2 and PD. Oh, you can also have another reagent. You can also use iron in the presence of water, and that will convert NO2 to NH2. And do you agree that this is reduction? You should, right? We removed oxygen, that's reduction. We added hydrogens, that's also reduction. And therefore, you get this product, which is called aminobenzene, or just so you know, it has a trivial name. The trivial name is aniline. You can actually also reduce a keto group. So remember that this is called an aromatic ketone. Based on our previous discussion, you can get an aromatic ketone via Friedel-Crafts acylation. And by mere use of H2 in palladium catalyst, you can actually just remove this double bond and it will become like this. As in, this is the final product, a mere alkyl benzene. So, of course, that's reduction because you literally cut off a single oxygen atom. And also, the moment that you have any double or triple bond here, we can actually treat this as if you are not really minding benzene, and you treat this as if it were a normal alkene or alkyne. So for example, I have this compound right here and I try to hydrate it. All we know is water will become H and OH. I'm going to put OH in the more stable carbon as per the Markovnikov's rule. And notice I'm speaking fast because you should already be aware of those at this stage. I'm going to remove the double bond and then my OH should go here as per the Markovnikov's rule. Meaning that they will act pretty much the same if the reaction is intended for the double bond instead of the benzene ring. Okay? Nothing special here. I mean, of course, there will be some special notes, but for most part, especially in basic course, in basic organic chemistry course, we can just treat it as it was just a normal double bond. Now, let's go back to the importance of knowing my meta directors and ortho-para directors. Look at these two. Here, I will try to show you what will happen if I try switching two exact same reactions. In both cases, I use this reagent, right? And I also use this reagent, but I just switch them up. And how will that influence our product? Let's see. First, in order for us to answer this, of course, you must have a background of our basic electrophilic substitution reactions. So if you forgot them, then you may want to review them first. But if you already know them already, by heart, or maybe enough to answer this. Let's go. So if I have this reagent, what type of reaction is this? I have an alkyl halide, and this is probably Friedel-Crafts alkylation. Wherein, what we try to attach is the entire alkyl halide minus the halide, meaning only these two carbons. This is just a catalyst. We don't need to attach it to benzene. And the final product is, how many carbons are these? 2, right? So the final product is, I just attach 2 carbons. We're done. That's the first step. Now, what if I use this reagent? So SO3 in the presence of H2SO4 is our classic sulfonating agent. And therefore, from here, we're going to add the electrophile SO3H, or what we used to call the sulfonium ion, this one, right? But now, of course, the question is, we have an initial substituent here, right? And remember, I told you a while ago, at the very start of this discussion, the moment I have one substituent on benzene, that substituent will dictate the direction of anything that's coming next. Here it is. So now, let's go back. Is an alkyl group like an ethyl group an activator or deactivator? Sure, let's go back if you want. And remember, an alkyl group is an activator. And what are activators gonna direct us to? Ortho and para. That means that my question a while ago was, where do I put my SO3H? Well, we just answered it. We're gonna put it in ortho and para. That's right. We're gonna have two products. One of them is the ortho product, right? And then the other one, you really have to draw it because there are two products, is the para product. But what if I tried to perform sulfonation first and then Friedel-Crafts alkylation next? Hopefully you can imagine what's gonna happen now. If I use this, of course, that's the first thing I will attach. But now, the moment I try to alkylate, where will it go? The fact that SO3H is a deactivator, right? Then therefore, it is a meta director. Only meta, only one position, meaning I will only have one major product, and that is the meta product. And the meta is either here or here, right, relative to this carbon. So I'll just choose this. I mean, it doesn't really matter if I put it at the left. I'll just put it at the right. I don't know. I have space here, so why not? So there's no other product. So this is the only major product here. So notice the difference. You use the same exact two processes or steps. Yet, when you switch places with them, I mean, when you switch their order, then you get something that is not even the same as the first two. And that's the importance of sequence, my friends. For example, just to practice ourselves, I have here a scenario wherein I start off with plain benzene and I subject it to 3 reactions. And I want to get this product. You can pause and think if the proper sequence is the green one or the yellow one. Only one is correct because the other one, which is wrong, will not give you this answer. Try it out. Pause it now. If you don't want to pause, then I'll answer it now. So let's see if the green one will make sense. Maybe let me erase everything just to have some space to write on. Maybe here for a lot of space. So if I try to use this first, alkyl halide, right? So this is Friedel-Crafts alkylation. I will particularly attach the methyl group, and then I subject it to oxidation. Remember, what we're gonna do is we're just gonna convert this alkyl group to COOH, right? Using KMNO4. So that will become COOH. And then I add this one. This is chlorination, meaning all I need to add is a chlorine atom. But where? Well, you gotta ask, is this an activator or deactivator? And of course, COOH is listed under our deactivators. So meaning this is gonna be a meta director. And therefore, we're gonna put our chlorine here. Anyway, what is this in the first place in terms of orientation? Is it ortho, meta, or para? This is placed one carbon apart, right? So this is meta. And the fact that this is meta and your product here is meta, that means that this green sequence is actually the correct sequence. So does it mean that there's no way I can get the meta product if we use the yellow one? Well, why don't we try it out? Let me erase everything again. So let's try chlorinating it first. So of course, the first thing I add is Cl. And then I alkylate. Of course, I'm going to attach the CH3. But where? What type of director is a halogen in the first place? Oh wait, that's right. A halogen is orthopara, meaning that I'm going to put my CH3 ortho and I'm going to put the other product para. And all KMNO4 would do is to just convert those CH3s to COOH. But even in that case, is any of these two products a meta product like the one we're looking for? This one is ortho, of course not. Para, so no. So that means it's really true that this sequence cannot give you the meta product. And therefore, the only acceptable answer is this. So hopefully this demonstration kind of emphasized to you how important the proper order of reactions are, especially for benzene, considering the multiple effects of orthopara activators and deactivators as well as all meta deactivators.